All right, here we go. We have the official report here for the Omni-Pod Mark II. Again, the Omni-Pod Mark III, we go much deeper as we kind of refine our template, and a lot of our other ideas we have, I don't know, I'm pointing over here. A lot of our other ideas, we have our template that we go kind of improve over time. So we're going to have a lot more content, a lot more well-rounded approach to the new idea. This one essentially is one that had done for a while. I just didn't realize I didn't have a video for it, and I realized I need to keep up with my videos a little bit more. But let's go ahead and delve into the Omni-Pod Generation 2 Ergo-Bubble Model 2. The photo, the Omni-Pod equipped with a single metallic tire rotating above an electromagnetic highway platform. So you can see what I'm saying. First page of the report. Let's see if I can read this over here. I want you to see what I'm seeing, but I can just show the picture. When I'm done, you can see the picture. Or I can try to, actually, I'm going to try to see if there's a way to publish the report on social media or add a link to it. So maybe save it, not as Microsoft Word, but something else. I'll try to figure out, I'll try to make it available for, so you guys can see it too. So something available for your eyes so you can follow along. So yeah, I need to figure out how to do that. Just go ahead and ask the prompt while I'm thinking about it. Go ahead and submit the prompt and then pin it just in case it goes away. Hey, so I have full reports written for several ideas, but I'm not sure how to add those links to social media or how to change the file or alter it. So basically it's accessible to through a link. What platforms would you recommend, or how would you recommend going about that? To like add links to like YouTube, Facebook, and other social media like Instagram, Snapchat, or whatnot.
In a way that generates a shareable link. Google Drive is a great and secure option for this. Once you have the file link, you can share.
Drive. Okay. So Google Drive, I figured it's something Google seems to have a lot of the tools, except for this Google. This Google doesn't seem to be answering anything. This one, it's been struggling for a while. I don't know if it's internet access or what. That's weird. Anyway, so we're going to get into the Omni-Pod Generation 2 Ergo-Bubble Model 2. The prototype design concept. Oh, hold on. That's crap. Still listening. All right, prototype design concept. We have a photo of the Omni-Pod with additional features. However, this one includes a very thick tire, just for display purposes or for visual purposes. Note that it would be much more energy efficient, though, if it were instead split up into at least 2 or more smaller wheels to reduce the amount of torque required to rotate them. The Mark II design has 2 up to 4 large but very thin wheels that fully encapsulate the bubble pod inside of it, wrapping around the front, top, rear, and bottom of the vehicle. The wheels only cover about 10 to 20% of the entire vehicle frame, leaving plenty of room for passengers to view the outside environment and surroundings. Each wheel is about 6 inches, up to 1 foot in width. They are thin, so the amount of force required to make them rotate is minimal. A single thicker wheel would require much more force to turn. Using a series of thinner wheels also allows each of the wheels to rotate at different speeds, which makes it easier for the vehicle to turn or pivot as needed. The 360-degree rotation or spin in place feature is compatible with this concept as well, just like it was for the Omni-Pod Mark I. Just a different design for it. So again, looks kind of more like that, where the wheel wraps around it instead of being on the bottom, and then the rest of the vehicle is being kind of like squat. Pretty big overhaul on the vehicle design here. To get the vehicle to spin in place, the right wheels and left wheels simply spin at the same speed but in opposite directions. Using this feature will make the entire vehicle look like a large coin spinning rapidly around on its side. Obviously, units which are sold commercially will require an artificial rotational velocity limit for safety. However, prototypes may rotate freely during testing to monitor the structural integrity of the design during initial R&D or research and development phases. The wheel tilt feature. To assist with turning, the section containing the wheels or tread can tilt while the main cabin where the pilot and passengers are seated remains upright thanks to gyroscopic stabilizer mechanisms integrated into the pod's design. The bubble pod itself remains upright while the surrounding wheel tilts left or right to make turning much easier. For the gyroscopic stabilizer mechanisms, to stabilize the Omni-Pod, we need to move from commercial, off-the-shelf products to fundamental engineering principles. Gyroscopic stabilization is a viable high-tech solution for inherently unstable vehicles like a bubble pod or a motorcycle. Gyroscopic stabilizer technology varies in size from microchips to heavy industrial flywheels. Here's a breakdown of the smallest stabilizers on the market by category. So some options we can use for this. We have some that are used for boats or marine stabilization, such as Quick Gyro Mk II X2, while the Seakeeper 1 is often marketed as the industry standard for small boats. The Italian-made Quick Gyro Mk X2 is physically smaller and lighter. For application, stabilizing small recreational boats, approximately 20 to 30 feet, to stop them from rolling in waves. Weight is about 289 pounds or 131 kilograms versus the Seakeeper 1 at about 365 pounds or 165 kilograms. The dimensions, it's roughly 16 inches by 16 inches by 19 inches, compact enough to fit under a seat. The mechanism, it uses a vertically spinning flywheel to generate anti-roll torque. For satellites or aerospace, the CubeSat Control Moment Gyroscope, or CMGs. CubeSat Control Moment Gyroscopes, CMGs. This is the absolute smallest mechanical stabilizer mechanism in existence. These are miniature flywheels used to orient CubeSats or nanosatellites in zero gravity. The product example is TensorTech CMG 10M or ViaWare Mini CMG. The size, it's comparable to a tennis ball or a soda can. Mechanism, a tiny spinning rotor mounted on a motorized gimbal. When the gimbal tilts the rotor, the gyroscopic torque rotates the satellite. I placed an image here. It says various colored Omni-Pods traveling across various environments to exhibit its resiliency and adaptability. For mounted interior or exterior cameras, for the we recommend the DJI Osmo Pocket 3, or at least it's an example. For standalone stabilizing device, this is the smallest integrated system. The size, it fits in a pocket, approximately 6 inches long. Mechanism, it uses a three-axis motorized gimbal for active stabilization rather than a heavy flywheel for passive stabilization. An honorable mention, a mechanical version is the Quinton Gyro KS2, a true mechanical gyroscope, a heavy spinning brass wheel used to stabilize handheld film cameras or binoculars from helicopters. The product is the Quinton KS2. The weight is about 1.5 pounds. The mechanism used is two spinning tungsten wheels at 20,000 RPM. It resists motion rather than correcting it electronically. We have system interface compensation for human tremors, medical grade. And this would be the Gyro Glove by Gyro Gear. This is an integrated or wearable stabilization device designed for people with Parkinson's or essential tremors. The mechanism, it features a high-speed mechanical gyroscope attached to the control panel or the back of a glove. The angular momentum of the spinning disc fights the user's hand tremors, keeping the hand steady. The size, the mechanism is roughly the size of a hockey puck. The size and weight of a gyroscopic stabilizer are directly proportional to the angular momentum it needs to produce. This is the stabilizing power, which must be large enough to counteract the largest disruptive force or torque your pod will encounter. The key formula for stabilization, the required stabilizing torque or torque symbol is defined by torque equals inertia or moment of inertia times angular acceleration. The stabilizing gyro must produce a counter torque, which is proportional to its angular momentum, where h, the angular momentum, equals moment of inertia of the gyro's flywheel multiplied by the angular velocity or speed of the flywheel measured in RPM. The estimated pod weight or displacement. The gyro system is only 5 to 10% of the vehicle's total mass, higher than the 2.5 to 5% ratio found in marine stabilizers, but necessary for a vehicle that is inherently unstable. In other words, a spherical pod and must stay upright at 0 speed. The pod structure or shell would be estimated to be about 300 kilograms or 660 pounds. The human occupant would be about 100 kilograms or 220 pounds. The batteries or motor and tech would be about 100 kilograms or 220 pounds. And the total system mass would equate to about 500 kilograms or 1,100 pounds. Stabilization ratios. In the marine industry, the weight of the gyro stabilizer is typically 2.5% to 5% of the vessel's displacement or weight. Minimum stabilization requirement, 2.5%. Calculated gyro mass, 12.5 kilograms or 27.5 pounds. High stabilization requirement, 5%. Calculated gyro mass, 25 kilograms or 55 pounds. Size and dimensions. For a 500 kilogram Omni-Pod, we would likely need a gyro stabilizer with a total unit mass between 12.5 kilograms and 25 kilograms. The core component, the flywheel, must be massive enough to store the angular momentum necessary to fight external torque. For example, wind gusts, uneven ground, sudden occupant shifts. If the flywheel is too small, it won't generate enough force to quickly correct the pod's lean. Safety feature redundancy. The system uses twin counter rotating flywheels. This is crucial because it cancels out the gyroscopic effect along the vehicle's yaw or turning axis, preventing the steering from competing against the gyro when the vehicle turns. Required torque. The 800 Newton meters of torque is a massive amount of corrective force, enabling the vehicle to self-correct even after a significant lateral impact. Simulated accidents show it stays upright. Overall analysis, gyroscopic stabilization for road vehicles faces 3 major hurdles. 1, the square cube law, or mass versus torque. 2, stabilization skills with angular momentum, which is proportional to the mass of the flywheel, and rotational speed. As the vehicle's mass increases by a factor of x, the size and mass of the required stabilizing flywheel must also increase significantly to fight the magnified forces like centrifugal force, wind load, etc. We have a formula here. Required stabilizing torque is, I remember what that was. It was like proportional to the vehicle mass times disruptive acceleration. Competition with existing technology. Active stabilization in cars and trucks is already handled by mature technologies that are much lighter and more cost effective. For example, electronic stability control, or ESC, uses brakes or throttle to stabilize. Active suspension systems use hydraulic or magnetic dampers to counteract body roll in milliseconds. For inertia and steering, gyros that are powerful enough to stabilize a large mass create an opposing force called gyroscopic resistance. When the vehicle turns, the large spinning flywheel would actively resist the turn, making the steering feel sluggish and unresponsive, or requiring a massive or requiring massive complex actuators to overcome this resistance. This is why some vehicles use two counter-rotating gyros to minimize this effect. The energy required to rotate the wheels. The force or energy required to rotate a wheel is typically calculated as torque, which is the rotational equivalent of linear force. The primary formula needed for relating the required torque to a wheel's size and mass is Newton's second law for rotation. Net torque. The rule is rotational analog, It is the required rotational force or the output we are solving for. This includes all factors. Unit is Newton meters, or N, capital N, little m, Newton meters. For a moment of inertia, the rule is rule of rotational analog. This is the resistance of the wheel to changes in its rotational motion, analogous to mass. The dependence is mass, m, and radius, r. Unit is kilogram meters squared, or kg times m squared. Angular acceleration, the role or rotational analog is this is the rate at which you want the wheel's speed to increase, analogous to linear acceleration. The dependence is time and final speed, while the unit is radians per second squared, or rad divided by s squared. The total torque calculation. When rotating a wheel on the ground, as in a vehicle, the total torque required is the sum of two components. One, the torque needed to accelerate the wheel itself, and two, the torque needed to overcome external resistance forces, which accelerate the entire vehicle. Acceleration torque. This is the torque needed to get the wheel's mass spinning up to speed. Moment of inertia, or I. This is the key factor where mass and radius come into play. It depends on how the mass is distributed. For a solid disk, like a simple flywheel, use I equals 1/2 times m times r squared. For a thin hollow cylinder, like a bike wheel rim, use I equals m times r squared, where m is the mass and r is the radius. Resistance torque. This is the torque needed to overcome external forces acting on the entire system, and is typically the largest component for vehicles. The formula we use would be torque equals force times resistance. This is calculated by converting the required linear force F into rotational torque. The rolling resistance equals which is labeled by F rolling, is the force needed to overcome the deformation and friction between the tire and the ground. This depends on the wheel radius and the surface or tire material. Aerodynamic drag equals the force needed to push the air out of the way. This depends on the vehicle's speed squared, its cross-sectional area, and the air's density. Grade resistance equals the force needed to climb a hill. This depends on the vehicle's total mass and the slope of the angle. The final torque you need is affected by virtually every characteristic of the wheel and vehicle it is attached to. Mass and radius, or wheel geometry. This determines the moment of inertia. Desired acceleration. This is how quickly you want to reach top speed. For tire and surface friction, this determines rolling resistance, or F_rolling. Vehicle speed and shape. This determines aerodynamic drag. In other words, F_drag. And vehicle mass and slope determines grade resistance, also referred to or labeled as F_grade. Calculating rotational energy or work. While torque is the force needed to cause rotation, work, or W, is the energy transferred by that torque over a certain angle. This is the figure that tells you how much energy you're draining from your batteries. The formula for rotational work is the analog of linear work, or W equals F times D. W equals torque times change, or an angular displacement. So we got work or energy required measured in joules equals the torque applied measured in Newton meters. times the angular displacement, or how far the wheel rotated, measured in radians. The truly critical factor for a vehicle like the Omni-Pod is power. Power is simply the rate at which you use energy, or the rotational force applied at a given speed. We have power required measured in watts equals torque measured in Newton meters times angular velocity, or the wheel's rotational speed, measured in rads per second. This is the ultimate formula that dictates our design limitations. To accelerate our pod quickly with high torque while traveling at high speed, the motor must output a massive amount of power. This is why sports cars require high horsepower or high power engines, even though the total energy needed for a trip is the same regardless of how fast you drive. The instantaneous power demand defines the required size, cost, and complexity of the motor and battery pack. This energy or power concept ties directly back to the gyroscopic stabilizer idea. The gyro flywheel itself requires a massive initial burst of power to get spinning up to its operating speed of approximately 10,000 plus RPM. That power is purely used to overcome its moment of inertia. Excuse me. For run-up time, the greater the mass and radius of the flywheel, the larger the motor we need and the longer it takes to spin up to speed. Stabilization power. Once spinning, the gyro stabilization mechanism requires a continuous input of power to rapidly precess or tilt the flywheel's axis to produce the stabilizing torque. The ability of the motors to quickly move the heavy flywheel is what prevents our pod from tipping over. This instantaneous power delivery is why stabilization mechanisms must be incredibly robust. This is a calculation of propulsion power, or P underscore propulsion, which is the total power required by the motor to move the entire vehicle. For a 500 kilogram ergonomic bubble pod or Omni-Pod, the total power needed at any moment is the sum of the power required for acceleration and the power required to overcome resistance, such as drag, friction, and gravity. The governing power equation. The total power required at the wheel is given by the derivative of the total energy equation, which is P underscore propulsion with equals P underscore acceleration plus P underscore resistance, where P equals F times V, or power equals force times velocity. Power required to overcome resistance, or P underscore resistance. This is the power needed just to maintain a constant speed, calculated by converting resistance forces into power. In other words, the formula would be read as P underscore resistance equals, in parentheses, F underscore rolling plus F underscore drag plus F underscore grade, in parentheses, times velocity. Rolling resistance, the dependence is proportional to mass. Since our pod is relatively light, or 500 kilograms, this is manageable. It's the dominant force at low speeds below 25 miles per hour or 40 kilometers per hour. Aerodynamic drag, or F underscore drag, dependence is proportional to speed squared, or V squared, and frontal area, or A, capital A. Today's acceleration is capital A. This is the biggest killer for electric vehicles. If our bubble design is truly aerodynamic or has a low drag coefficient, power needed is lower. It's the dominant force at high speeds. For grade resistance, or F underscore grade, the dependence is proportional to mass and slope. A 5% incline dramatically increases the required power, as the vehicle must lift its entire 500 kilogram mass against gravity. For a real-world reference, for a 500 kilogram vehicle, light electric cargo trucks and L5 category vehicles, which often weigh 1,000 to 1,500 kilograms, but are designed for a 500 kilogram payload, often use motors with a rated power of 5 kilowatts to 9.5 kilowatts to achieve top speeds of 40 to 55 kilometers per hour or 25 to 34 miles per hour. If the Omni-Pod is highly aerodynamic and designed for moderate speeds below 40 miles per hour, we would need a minimum continuous motor power of 5 kilowatts to 10 kilowatts to sustain motion and overcome resistance. Again, we need to up that power, but that's just an example of like a minimum power required for like say below 40 miles an hour. So we jump that up to get it up to regular road speeds and even higher speeds than that once we can perfect the self-driving technology and get people out of cars. That's a separate issue. Let's get to like the halfway point and we'll kind of split this up into two parts. Power required for acceleration. This is the power required to increase the vehicle's kinetic energy, which determines its 0 to 60 time. P underscore acceleration equals mass times acceleration times velocity. Where so P power acceleration equals mass times the desired acceleration rate times current speed. The power needed to accelerate is highest at the end of the acceleration phase when V is maximum. To accelerate a 500 kilogram vehicle to a final speed of 28.6 meters per second or 60 miles per hour in 10 seconds requires an average acceleration of 2.68 meters per second squared. The peak power required just for acceleration, neglecting resistance, would be P equals 500 kilograms times 2.68 meters per second squared times 26.8 meters per second, which is approximately 36 kilowatts, which equals 48 horsepower. Okay. The peak power of the motor, the maximum output it can sustain for a few seconds, must be high enough to cover both the high speed drag and the acceleration demand. For sustained cruising at 40 miles per hour, we need a minimum of 5 kilowatts to about 10 kilowatts. For maximum acceleration of peak, require that they be boosted up, like I said, to about 30 kilowatts to about 40 kilowatts. A motor with a rated power of approximately 10 kilowatts and a peak power capability of 35 kilowatts would be suitable for moving the 500 kilogram pod forward with reasonable performance. We got another image here of the Omni-Pod equipped with life support systems capable of space travel traversing the surface of Mars. The example of it in space, basically fully encapsulated, has pressure systems and life support systems in there. Futuristic design. So that concept right now, but definitely usable. We definitely do that for even like space tourism or on the moon. There we go. We can have this by the time we have bases on the moon. Let's make it happen. Let's do it. The world needs it. The world's really, really wants it. Not needs it. All right, for the technical specification sheet for the Omni-Pod Mark II, this technical spec sheet is designed to be a leave behind or a deep dive slide in a pitch deck. It provides the engineering proof of work to back up the sleek design of the Omni-Pod Mark II. Project name, Omni-Pod Mark II or Ergo-Bubble Model 2. Omni-Pod Mark II or Ergo-Bubble Model 2. Speaking too fast. Classification, personal electric transporter, or high stability L category. Core innovation is in encapsulating, thin wheel drive, and gyroscopic leveling. Oh, sorry. Feature 1, the total system mass is 500 kilograms or 1,100 pounds with a 300 kilogram shell, a 100 kilogram occupant, and a 100 kilogram technology integration or system or package. There we go. Feature 2, drive configuration, dual or quad encapsulating wheels, 6 inches to 12 inches in width each, high radius, thin rims. Feature 3, the chassis, would include a gyroscopic suspended pod and cabin, a cabin that remains upright during the plus to minus 30-degree wheel tilt. Feature 4, maneuverability. We have a 360-degree zero radius turn to allow for a 360-degree zero radius turn and counter rotational spin in place capability. And for the stabilization system, or the gyro core, the Mark II utilizes twin counter-rotating flywheels to provide passive and active stability without outriggers. Corrected torque is 800 Newton meters. Flywheel speed is 10,000 plus RPM. Stabilizer mass is 25 kilograms, or 5% of the total mass. And system mechanism would be twin unit setup to cancel unwanted yaw axis resistance. And as mentioned up above, reiterating it, emphasizing it, the balancing equation, the stabilizing torque required to fight external forces such as wind or shifts is governed by formula. So is governed by the following formula, where torque equals the moment of inertia times the angular acceleration of the pod's tilt. The gyro produces counter torque proportional to its angular momentum. So just looking at the, sorry, I was looking at the format to make sure it didn't change anything. Okay. Propulsion and power dynamics. The Mark II is optimized for high efficiency, urban cruising, and rapid response acceleration. Rated power for cruising is 10 kilowatts, approximately 13.4 horsepower. Peak power or acceleration is 35 kilowatts to 40 kilowatts, approximately 50 horsepower. Max velocity is 26.8 meters per second, or 60 miles per hour. Acceleration would, for the 0 to 60 miles per hour, would be 10.0 seconds, or acceleration would be equal to 2.68 meters per second squared. Propulsion math. To calculate the total power required at any moment, we have a formula: P underscore total equals F underscore rolling plus F underscore drag plus F underscore grade plus F underscore acceleration. So you got the rolling, force of rolling, drag force, and the force of the grade, that resistance plus the acceleration, that's all in parentheses, times velocity. For wheel efficiency, by using high radius thin wheels, we maximize the moment of inertia of the drivetrain components. I have a formula here that represents that. I underscore wheel equals M underscore wheel times radius squared, which I believe was the inertia. Moment of inertia is approximately the mass of the wheel times the radius squared. It was. Just want to make sure I'm not switching up my variables. Just trying to keep it consistent, so I've got everything correct. All right. So if anybody else is viewing it, can know what's going on there too. Because the wheels are thin, M, or mass, is minimized, allowing for faster response times and lower energy draw during start or stop cycles. Dynamic handling, the spin in place feature. Ooh, this one's the fun coin spinning feature. Dynamic handling, the spin in place feature. The Mark II achieves a spinning coin effect by decoupling the wheel speeds on the left and right axes. The turn mechanism, independent variable rotation. Pivot point is central geometric axis. Torque application, we've got a formula. T underscore net is, let me just read it here. A rotational velocity limit is digitally enforced for commercial safety, while R&D units allow for high RPM structural stress testing. We got the net torque equals, I don't know what that is. The sum of, there we go, that's what is it, sum of torque on the left side minus the torque on the right side. Efficiency and thermal management. For aerodynamic drag, C_D, this is the optimized spherical teardrop profile. For regenerative braking, use dual motor energy recovery. And for run-up time, use stabilization, or we have stabilization flywheels that require a 120-second initial spool up to reach operational RPM. Engineering executive summary. The Omni-Pod Mark II leverages high radius geometry to solve the heavy wheel torque problem while using aerospace-grade gyroscopic stabilization to allow a spherical cabin to operate on a thin track footprint. This results in a vehicle that is mathematically more maneuverable and energy efficient than traditional four-wheeled electric microcars. Viability note, the spinning coin effect. From a physics perspective, because the Mark II has up to 4 thin wheels, it can achieve a pure couple of forces. By spinning the left side forward and the right side in reverse at high RPMs, the Mark II would have the highest rotational velocity of any land vehicle in its class. The marketing hook, the spinning coin demo. For a launch event, imagine a dark stage with a single spotlight. The Omni-Pod Mark II is in the center. First, the stabilizers hum to life. This is the 120-second spool up. 2, the pod begins to spin. Step 3, it accelerates its rotation until it's a blur, appearing exactly like a silver coin spinning on its side. 4, it suddenly stops on a dime, the door slides open, and the pilot steps out, perfectly balanced and dizzy-free. For the user experience scenario 1, the impossible urban parking spot. We have a location here, a densely packed street in Tokyo or Manhattan. The problem, a standard EV sees a parking spot that is only 6 inches longer than the vehicle itself. A traditional parallel park is impossible due to the turning radius required. The Omni-Pod solution, first is the pivot. The pilot drives parallel to the spot, stops, and engages coin mode. The move, the wheels spin in opposite directions, rotating the pod 90 degrees on its center axis. The pod then simply drives forward into the spot. The exit, when it's time to leave, the pod rotates 90 degrees again and drives straight out into traffic. No more multi-point turns or blocked lanes. User experience scenario 2, the Sedona Red Rock Sunset Tour. The location is a steep, winding mountain resort trail in Arizona. The problem, traditional SUVs feel top-heavy on inclines, making passengers nervous about tipping, and the thick pillars of the car block the panoramic views. The Omni-Pod solution, gyroscopic confidence. As the path inclines and tilts laterally, the twin flywheel stabilizers engage. The passengers remain perfectly level or upright while the wheels tilt to follow the terrain. Unobstructed view. Because the Mark II wheels only cover about 10 to 20% of the frame and are only 6 inches wide, the passengers have a 300-degree panoramic view of the red rocks. The experience, it feels like floating through the landscape rather than being trapped in a metal box. User experience scenario 3, the Silicon Valley corporate campus. Location is a sprawling tech headquarters, for example, the Googleplex or SpaceX. The problem, executives need to move between buildings quickly, but the pathways are narrow and shared with pedestrians. A golf cart is too wide and unrefined. Yeah, here's the thing. So this is an example for a much, much smaller, like one person. So I don't think I clarified that, but this particular scenario explains the concept of one of the ideas I had for a one person, one passenger, lot smaller version. That is probably even open. So on the sides, you don't have it fully encapsulated. You can actually kind of stick out with just the thing going over you, or you can modify the design somehow. But I just want to clarify that because not all of them are going to be like golf cart or smaller size. They're going to be bigger. Going to have like those living room spaces and everything that was mentioned for the Omni-Pod Mark I. So again, different variants offered even within different has its own variants. Model 2 has variants. Model 3 has variants. And so there's like sub variants of each class or category of vehicle of Omni-Pod. All right, anyway, where were we? All right, the Omni-Pod solution, for pedestrian harmony, the Mark II's narrow footprint enabled by the thin wheel design allows it to glide down pedestrian walkways. Again, pedestrian walkways are still pretty thin. 2 is going to be pretty big, so like you could go by yourself, but I'm like, it's not like you need a wider pathway, like say something like Central Park or something like that, where it's at least like 20, 30 feet wide, and like that's fine. You can go in those pedestrian areas, or at least if you can go in areas if it's at least like say 10 to 15 feet wide or something like that. So maybe not all areas, but some we can work with that. So, and then we can modify designs as we go to more. The social rotation. If the pilot sees a colleague on the sidewalk, they don't have to crane their neck. They tap a joystick and the pod spins 45 degrees in place while still moving forward, allowing for a face-to-face greeting without stopping or veering off path. We have the statement. The Ergo-Bubble aesthetic perfectly matches the high-tech branding of a tier 1 tech firm. Right on, man. Yeah, you don't want to be using lame golf carts. You want to be using the Omni-Pods. Man, who uses golf carts to get around? It's so 1990 or early 2000s. Ugh. Step into the future, man. All right. User experience scenario 4, the accessibility hospital transfer. So this one will be important and very useful. Location, a massive multi-wing medical center. The problem, moving patients or doctors between wings requires long walks through narrow corridors and frequent 180-degree turns at dead ends. The Omni-Pod solution, zero radius reversal. In a hallway that is only as wide as the pod itself, the Mark II can perform a 180-degree spin and head back the way it came. For precision docking, the pod can rotate so the door is perfectly flush with a hospital bed or a building entrance, making entry and exit seamless for those with limited mobility. Silent stability. The electric 10 kilowatt motor is silent and the gyros ensure that even if the floor is uneven, the bubble remains rock steady, preventing motion sickness or other disruptions, preventing injury. So about 45% here, almost there. Manual override features. Controlling a vehicle that can spin like a coin and move omnidirectionally requires moving past the traditional steering wheel and pedal setup. Since the Mark II design features wheels flush across the entire sphere, the pilot needs to manage 6 degrees of freedom or 6 DOF, moving up or down, left or right, forward or backward, and rotating on 3 axes. Here are 3 distinct interface concepts for the spherical Mark II vehicle. First, we have the orbital haptic trackball or manual physical feature. Instead, so orbital haptic trackball is like something like that. So like a ball goes like that and spins, you go like that, something like that. It's like there's games like that where I think of those golfing arcade games. It's like a little ball, but this one could be like a bigger ball where you can like both of your hands like have more control over it too. So higher surface area from your hands and more control. All right, so for the orbital haptic trackball, instead of a joystick, the pilot uses a weighted motorized sphere, roughly the size of a grapefruit, floating in a magnetic cradle. Again, like I said, for more control, you could have it bigger, but say for faster movement, say for like say high performance racing versions, you could have like a much smaller ball, but like something like that. So it's basically like kind of like the drivers look like a disc jockey, like. We're good, stupid. Okay, how it works. The pilot places their hand on the controller. To move the vehicle forward, you push the ball forward. To spin like a coin, you flip the ball into a spin. Haptic feedback. Because the Mark II design uses flush wheels, the controller would provide a surface resistance. If the vehicle is off-roading, the pilot feels the vibrations of the individual wheels through the ball. The drift toggle, a trigger on the cradle, allows the pilot to decouple the cabin's orientation from the shell's movement, allowing the sphere to roll at 100 miles per hour while the pilot stays perfectly level. 2. The synaptic ghost link, or neural mind link. In this scenario, the pilot wears a non-invasive BCI, or brain-computer interface headset. This is ideal for the high-speed, high-torque, 800 Newton-meter maneuvers we've envisioned. Sorry, correcting that. The concept: the pilot doesn't drive the sphere, they become the sphere. Be the sphere! The brain treats the vehicle's outer shell as its known skin. Oh, I was thinking of a reference like, be the ball. Be the ball. Is that one movie with Tom Hanks? All right. I'm easily entertained. I make myself laugh. It's fun. Brain treats the vehicle's outer shell as its own skin. Proprioception: the pilot feels the friction on the wheels traversing the sea floor or an asteroid or mountain. If a vehicle loses traction on a dark mine wall, the pilot feels a numbness in that sector of their spatial awareness. Response time: near zero latency. For maneuvers where the sphere needs to change direction 180 degrees instantly, the mind link can trigger the reverse torque faster than a physical hand could move. Vector-based AI autopilot, or augmented control. Because managing wheels all around the sphere is mathematically complex, the pilot provides intent while the AI handles execution. The interface: a holographic HUD, or heads-up display, that projects a vector arrow into the environment. So basically, as you're driving, you see like, for some reason, the first thing that comes to mind is the Simpsons Road Rage video game, where it has like a finger that just points to where you need to go. I mean, you can have something like that, or like an arrow or something, or even on the ground have like arrows that mark the trajectory of the vehicle, depending on if this is the brain interface. Thinking about where you want to go, it projects an image, like say red would be like really fast or dangerous, and then green would be like slower and safer, or more certain of a projection of angle, velocity, and all that the computer calculates, displays on the heads-up display system. Or you could even have something just as, so you could have those like marked as labels over here, even little dots that mark the trajectory and then even indicate speed or risk. And then, like I said, you could also even have something as simple as just like an arrow just pointing to where you need to go with a little compass symbol like N, S, E, or W for compass directions. All right. So where were we? Point and go. The pilot points their hand or eyes at a location, kind of like these, what was it, the Apache helicopters with the gunner, the turrets, something like that. They point their hand or eyes at a location, for example, a ledge in a dark mine, and the AI calculates which of the flush wheels need to engage and at what specific RPM to reach that point while maintaining the desired spin. Stabilization. The AI automatically manages the 800 Newton meters of torque to ensure the vehicle doesn't flip uncontrollably when hitting an obstacle, essentially acting as an advanced electronic stability program, or ESP, for a 3D environment. 3, the gimbaled cockpit necessity. Regardless of the control method, we need to address the pilot's physical state. If the sphere is rolling and spinning in space or an underground tunnel, the pilot's inner ear would be destroyed by the rotation. So we need a triple axis gimbal. The pilot's seat is suspended in the center, staying level while the outer shell spins 360 degrees. We would require possibly liquid immersion. This would be for space or high G maneuvers, definitely not standard editions. So for space or high G maneuvers, the pilot is suspended in a breathable fluid to offset the centrifugal force of the coin spin. I don't remember what that was. Specify that I know in the Mark III idea. I remember that's definitely in there, and we clarify that. I don't remember what the word for that was, or what the substance was called, that fluid was called. It's in the Mark III. I had it in there. We researched it. I remember researching that. That was pretty interesting. All right. Anyway, synthetic vision. Instead of windows, consider using an interface, which is a 360-degree screen projecting a see-through view of the outside, or a completely unobstructed view. In this instance, kind of like the Las Vegas dome, just much smaller. In this instance, in order to make a 360-degree spherical vehicle viable, let's try that again. In order to make a 360-degree spherical vehicle viable, the interface must bridge the gap between a pilot sitting in a stable center and a shell that is spinning with massive torque, in other words, 800 newton meters. Here's how we integrate the visual awareness with the safety protocols required for high-stakes environments like deep space or underground mines. All right, we kind of hit the 50% mark. I'm going to go ahead and cut this video off. I need a lot of other work that I need to do, so I kind of got to prioritize that. But we will definitely come back to this and pick up on where we left off, including the heads-up display visuals, augmented overlays, safety systems, operations in space, operations in mines, life support systems, and a lot more exciting stuff. So we'll come back to that. Take a little break here, cap it off. I thought I was at like half an hour. Geez, that was almost an hour. Wow. Went a little longer than expected, but that is okay because we're getting the ideas out in the world and start engineering. Let's start building a better world. Dive into the future, man. Say go. See you guys in a little bit. There we go.